Welcome to Data Platform Summit 2020. It's virtual and round the clock, and I will be talking to you about cognition for applications, cognitive services, and mixed reality in action. My name is Andreas Erben. I'm the CTO for AI and mixed reality and CEO Americas of DNet. So about me. As said, I'm associated with DNet and run the US operations, and I deal with mixed reality and AI. I have over 25 years of experience, have been exposed to virtual reality already in the mid 1990s, but after that worked with all sizes and most types of companies because frankly there was no money in virtual reality in the mid 1990s and that was just for research. I have an extensive enterprise background and however, I love geeky technology. That's why I got back into the fun stuff when Kinect for Windows came out and when um, HoloLens 2 and HoloLens 1 came out. I'm recognized as a Microsoft Most Valuable Professional, short Microsoft MVP, and also as a Microsoft Regional Director. My contact information is below. So let's first talk about HoloRoo. Why do I want to mention HoloRoo? HoloRoo is an avatar, and we had HoloRoo created as a mascot for applications for startups that I was working with. Now, the idea was to have HoloRoo in three-dimensional space, and you see how cute it looks with the cute little eyes and the little fur. We wanted it to look like in Zootopia. Now, there was a big difference when we got HoloRoo back and put it in 3D for the first time in front of us. It was surprising. We were, in a way, almost like taken aback. It felt uncomfortable, and it took us a while to figure out what it was. So there was this kangaroo standing in front of us, 1 meter 60, 5 foot something tall, and um, looking at us with his cute little eyes, but something was off. It has a substantial figure. I mean, it's not a small kangaroo as it stands there in front of you. But the most important thing that we figured out, it has claws. Yes, it's an animal. The artist in 3D built claws in. You will see HoloRoo in a video later on. So we went back to the artist and he was a little bit hurt, but he removed the claws and that made a big difference. Why do I tell you this? In our talk, we're talking about three-dimensional applications and applications that interact with your space. That matters. You need to be respectful of the space that you interact with users in. You're not in 2D anymore, this is 3D world. Be respectful of user spaces. But let's take a step back. Where do we come from? Right? This has not been too long ago in historical context. The first computers, it was a big thing. You could program a computer here by plugging wires in a different way. And then you have punch cards that were able to change a computer program rapidly compared to before. But it wasn't as modern, of course, as today. But it was a big innovation step. And another big innovation step was the first terminal, where you have a computer screen and a keyboard, and you could interact with the machine in text form. Then, look at this, the mouse. The mouse was invented in 1963, and the first terminal with a graphical user interface and a mouse was introduced in 1968. This has been a long time ago. Yeah, we're talking about 52 years. Now, the other thing is, you might say, touch. Yeah, well, touchscreens have been also invented in the 1960s. In 1965, the first touchscreen was introduced. Granted, a different technology and not as mobile and nice as today. And even the first concept of a smartphone with applications was introduced somewhere between 1992 and 1994, depending on how you count, with the Simon. So what has changed? We have bigger screens, we have smaller screens, we have fancier screens, they look nicer, or you can put them over the wall, you can carry them around with you, but basically we still work with computers like you would have worked in the 1960s 1968 time frame for the most part. Now let us talk about reality. We have a physical reality and a virtual or digital reality. What does that mean? The physical reality is what really actually exists. That is you looking at this recording right now and interacting with me as a speaker and other audience members maybe in the DPS conference. Yeah? That is you who are hungry, who can hear the noises around them, who may be distracted, who may be tired of staying home and wants to go out. On the other hand, the virtual reality, that would be you're replacing the physical reality maybe with something virtual. Those are the pixels on the screen. This is when you put on a headset and see something in 3D in virtual reality applications, but it can be anything you replace or recreate digitally. It could even include smell, touch, or other senses in the future. So, between the physical reality and the virtual reality, that is what we call mixed reality. It's when we blend those two worlds. You add virtual objects to the physical reality, or you interact with the virtual reality from the physical reality. Looking at it a little bit more complete, we have three different things here. We have the human being, that is you. We have the environment, that's where you are right now. And the computer that interacts with both of them. Traditionally, the computer and the human would interact in what we call human-computer interaction. That's the keyboard, the mouse, or maybe relate to speech recognition and other interaction mechanisms. Then you interact with your environment just in the conventional reality. Maybe you're thirsty and grab a cup of water right now and have a sip. That is conventional reality. Now, computers can also interact with the environment. They may have sensors and get an understanding of the environment, and that's what we call perception. When computers understand the environment or try to understand the environment, it is called perception, and together, all this together is called mixed reality. The end goal, of course, is not just to make technology. The end goal is to have all this to better understand what you as a human being want to do next, to get the human user intent for what you want to do next with the computer. Now, the spectrum between physical reality and digital reality has virtual reality on one extreme, where you replace pretty much everything of the physical reality by virtual objects, or it has augmented reality on the other end, where you just add a little bit of additional things to the real reality. Like, it could be as simple as a heads-up display. Even an Alexa could be called augmented reality in a way because it adds audio context to your environment. But more practically, people talk about like apps on your phone where you may get information about something your phone camera looks at. The mixed reality is the whole spectrum in between. Yeah? See-through displays like HoloLens and so on. So what are the building blocks of all this? Right? To build applications that interact with the real world, with space, you need to have a concept of space and some things you interact with it. You have gaze, that is, in which direction is my head pointing as the most minimal part, like a virtual arrow pointing out of your middle of your forehead in a direction. And so a computer can understand what you're looking at, or roughly looking at. Newer applications and hardware systems like HoloLens 2 have eye tracking built in that can also be used to and have a better understanding of gaze. What are you gazing or looking at? Gestures. Gestures is a way that you use your body to interact with your environment, and the computer can understand it. Or you gesture to the computer to trigger a specific command. That can be a very formalized gesture, for example, the so-called air tap that you had in HoloLens, or the bloom gesture. But it could also a more natural understanding of your gestures that was introduced in HoloLens 2, like grabbing a physical object, which was enabled by better hand tracking capabilities. Yeah, those can be gestures. Voice commands is whatever you say understood by the computer. Could be very, very predefined, start program, close window, or it could be a more natural flow of interacting with you in a type of agent, bot type approach, where the computer asks you questions and you respond, or it could really just understand what you're saying based on the context for future type of artificial intelligence driven voice understanding controls. GPT-3 comes to mind. Look it up if it interests you. Controllers are in this interesting part. Controllers enable you typically to do things that you wouldn't be able to do as well with your hands. This may be because the sensor technology may not be sophisticated enough yet to understand what you're doing with your body and your hands, but it could also be that the controllers allow you to do things with more granularity. Like if you have a joystick, for example, you could map the motions on that joystick to motions in the real world that are much, much, much smaller than this. So if you want to move something by just a fraction of a millimeter, then a controller could do that by mapping the controls of the controller to small movements in your real environment. Spatial mapping. This means your device recreates an understanding, a concept of the environment that it sees, of the 3D structure of it. It means there's a depth camera in HoloLens 1 and 2, for example, and this scans the environment and then is able to see, hey, there's a surface here. This surface here is connected to another surface, and so on and so on. And those surfaces can be further processed and maybe later understood and analyzed. For example, this is a tabletop, this is a floor, this is a ceiling above me, those are walls. And you can do those with those things then. Put something on the table, hang an image, a picture on the wall, and so on. Spatial sound is very important for realistic 3D applications. It helps you to more naturally interact with your environment and to locate objects. For a software developer, this is very easy. A software developer would just say in a modern software environment, hey, this virtual object we know has a 3D position and we want it to have sound. And the system will automatically render this audio to be spatially correct to wherever you're standing, so it sounds to you like it's coming from the left, the right, or even behind you. Finally, the concept of world coordinates. That is the ability of the system to understand where things are, like virtual objects, as they relate to real objects, and to load them back after an application restart. Like, I will not go much deeper into that, but this is a very powerful concept. Look up Azure Spatial Anchors, for example. And now we are back at HoloRoo. Remember the little kangaroo I mentioned before? That is it in front of you as looked through HoloLens. This application video recording will show you a little Easter egg hunt that we implemented just to demonstrate the capabilities to interact with the 3D environment. HoloRoo will follow the user around and keep a respectful distance from the user, and you will see Easter eggs scattered around. The important thing is the system dynamically learns as you walk around from what the sensors of the devices pick up, get a better spatial understanding of the environment, and then will hide Easter eggs over time in a more difficult position by constantly trying to find walls and see where have you been, how often, and where have you not been, where have you found eggs, where you haven't you looked for a while, and so on. Now let's start the video. So you see, HoloRoo has little cute animations. Yeah, and well, we're tapping on it. We follow it around, and do you see there's no claws, so it's not as threatening as it used to be. And it was hopping around, so it follows the user based on so-called breadcrumbs. Breadcrumbs is a concept where we basically, like in the fairy tale Hansel and Gretel, leave little markers on the floor, and HoloRoo will just follow us with a respectful distance, not getting closer to us if it's less than 2 meters. Now, you saw 2 Easter eggs here. The Easter eggs can just be activated when you click on them. and the Easter eggs disappear. Over time, as I said, the video doesn't show it, but Easter eggs will appear in different locations and finding them will get more and more difficult. Like, for example, they might appear in this corner here because we have never been here, and or they might be in a corner that we haven't even looked at yet. And as you find them, you explore the space, and as you explore the space, you scan more of the space, and so you gather an understanding of your environment. This video is important because it shows you a lot of different concepts of mixed reality, like not just adding objects like the kangaroo and showing an Easter egg as it explodes when you find it, but it also shows you the concept of, well, how to position objects on the floor, even if it's just on the floor, which is based on scanning your environment and interacting with the virtual avatar that follows you around. Please remember this video as we go back then to the more advanced scenario at the very, very end. Now for mixed reality, let's take a step back and look at what is AI. What is artificial intelligence all about? Artificial intelligence is really about helping us. It's about amplifying human ingenuity with intelligent technology. So there are different parts here. We have reasoning, learning and forming conclusions with imperfect data. We have understanding, interpreting meaning of data. That could be like text understanding, voice dictation, or images. And interact with people in natural ways. So all those things are things that also were very, very relevant for mixed reality applications. So Azure Cognitive Services is something that Microsoft built, coming out of the research branch initially, and basically productizing rapidly very, very advanced findings and innovations in artificial intelligence and deep learning. So it is all about applying AI to your business rapidly. So let's look at it briefly, what we get in Azure Cognitive Services. We have two areas, main areas. Remember when I talked about perception earlier? That is one area. And then there's comprehension. Perception deals more with the real world, and comprehension more about context and semantics. Right? So to categorize that further, inside of perception we have vision and speech, and in comprehension we have language and knowledge. Those are just a few bullet points at the bottom in the ever-expanding list of cognitive services that are available. So in vision-based services, it would be computer vision, for example, face emotion recognition, or more facial expression recognition, actually, optical character recognition, handwriting, custom vision, video indexing, content moderator. With speech, it could be custom speech, text-to-speech, speech-to-text. In language, however, it would be more understanding also the whole text translation, which takes into consideration more context, language understanding, text analytics, or making question and answers. And finally, knowledge, enabling searching, for example, like the Bing search engine does for you as a user. It can also be used for your enterprise data and expose your knowledge to people who want to understand what knowledge you have accumulated inside your own company. Now let's do a quick demo. This is the Cognitive Services Computer Vision portal, which gives you the information to get started with the service. So let's just look at what it can do for us, right? It can analyze an image, read a text, or recognize a celebrity. Let's just start with analyzing an image, uploading something. Let's say, hey, this is me drinking from a red cup. As you see, it recognizes here a person, and even tries to draw an object, rectangle around it. And behind the scenes, it actually gets back JSON data from that service. It's a RESTful service you call, but there are rich APIs for .NET/C# available, for example. And it thinks that the person, it's in situations indoors, there's a wall here, there's a human face, there are headphones there, and yeah, and somebody drinks a soft drink. Okay, so that's not too bad. Yeah. A little bit more frustrating is another thing that I tried earlier when I um, asked, hey, what celebrity might I be? And I used this picture here. And what did it find? Found a bunch of characters that says, hey, there's a 50% chance that this person is bald. I didn't like that too much. But in general, you see this is a general purpose service that can give you rich insights into your pictures you presented with to understand what's going on there. We will use this service in a more advanced scenario later on to get insights into a real environment and use those insights later on also for offline scenarios. Because remember, this is a cloud-based scenario. You can only use it when you have an internet connection and access to the cloud. Now let us see what we can do with custom vision. Really, really simple. We want to have a red cup detector. We want to train the AI to recognize me holding up a red cup that I'm drinking from maybe, and not, as in contrast, holding up my phone. We give it a name, we can skip the description here. We say we want to do classification and not object detection. Classification means we just want to find, is this a red cup picture, and not where in the picture is a red cup. And we expect it only to have one tag per image, meaning we're not expecting to find two red cups, or we're not expecting it to find a phone and a red cup in the image. The domain tells the system what to optimize for when it does its training. So the general domain is really when we don't know anything about what we're training for. The retail domain, for example, can optimize for typical things, how retail packaging typically looks like. It like a cereal box will have very clear colors, often large areas with the same color, and so on. While food has a color spectrum and maybe a contrast that's very typical for natural things, and landmarks, be it like landscapes or buildings, are also very typical in how they look like and how you can look at contrast and different visual properties. The compact domains we will not look at here in detail, just to tell you if you select this, then you can export it also to save for execution on a device as an Onyx model, for example. Right, go back to the general domain. Let's create the project. So in the project, we need to add the images. And here are some images of a red cup. We want to add those images and give it the tag that we want to assign right away, red cup, and the images get uploaded in the background. Okay, they've been uploaded successfully and have been tagged already, but we also want to have some other examples. We want to distinguish me with the phone from the red cup. Phone image, and upload those. You see on the left side how the tags are already assigned to those images. We can filter by the images by the tag. If you would have an image without a tag, it would show in the untagged images, and we could quickly tag it manually. After we're done with that, of course, we need to train. So we're choosing the quick training, which has some optimized settings to do the training run, and we'll check back with you as soon as the training is finished. As the training is finished, you see the results of the training run defined as precision, recall, and AP. I will not talk about those values in detail, but it gives you an idea how good our training is for the specific scenario that we trained for. It doesn't mean that it's good for slightly different scenarios. So that means, for example, if you would change any parameter like the background we had behind ourselves, when you look at the training images, they're all very similar, has the same background for all of them, then it might already confuse the system. But let's still see in a quick test how good our training is for detecting a red cup versus a phone in this specific background. So I separated out an image here. Let's start with the phone image first. Yeah, we selects the phone image, and it recognizes it as a phone image with 99.9% probability. And now let's look at the red cup image, and it says it's a red cup with 100% probability, which is a good result. As in contrast, if I would hold up, for example, a different cup with a different environment, it gets confused. I mean, it doesn't know what to do. It still thinks it's a cup, I mean, which is kind of true, because maybe it uses a shape for it, or if I use virtual reality headset, it thinks it's a phone image. I guess those objects have a little bit more in common in a general manner. But as you see, you can confuse an AI easily when you present it with something that it doesn't expect. I hope you like what you've seen so far. Now let us talk about Video Indexer. It's all about what's in your content. It's a service that lets you extract insights from video and audio files and uses advanced machine learning algorithms to do that. It is using Azure Media Services in the background and combines a lot of cognitive services and Azure Search to do all those things. You will see some of the pipeline in a later slide. So it's available for free in a free trial, and it is a platform as a service product essentially. So as you see here, it has a whole pipeline for audio analysis and video analysis, like mostly vision-based, of course. And those are combined here, right? I mean, for example, you have sentiment analysis and brand detection and so on and so on. I will not be able to talk through all the details in here, but you see this pipeline is really, really complex and really, really rich. I'm not saying it's a cheap service, but it enables you to do really advanced things with your videos. The feature set includes a lot of different things, right? In our talk here, we will look briefly on this here, brand detection. That gives you insights into where specific brands are in a video and what can we do to make it even better. Other features include, for example, identifying the language of a speaker, extracting visual representation of a video, of an image, of a thumbnail, doing transcripts in multiple languages and translation, and so on and so on and so on. Last but not least, things like shot detection to identify good like scenes and shots that represent your video. So we at DNet actually went a step further and found Video Indexer is great in giving you insights into brands, but we wanted to do more things. Like we wanted to find relevant videos to specific mentions of a brand or brand imagery of those brands in the video. We wanted to get a good visual representation of a brand in a video, not just a mention, and find the location of the video maybe in a larger video to then position a brand-specific advertisement for the customers who might be broadcasters and want to sell advertisements to brands based on the content they're showing. The solution would be to use Video Indexer to get insights based on OCR and speech, use computer vision to find many brands and logo variations, and then custom visions to really dive deep into specific brands and specific detection of brands and products or custom objects. And we look at that in a second in a demo. The way it flows is we have a little demo app here, basically, that is UWP based, gets insights from a video. It's a RESTful API with Video Indexer, then uses a brand insight that is based on OCR and speech to get the results from Video Indexer, but also at the same time extracts the keyframes from the video. Keyframes are good visual representations of specific scenes that are also non-blurry, which is very important from a video. Alternatively, we also use fixed distances, fixed intervals to get, for example, a snapshot of the video every second or every tenth of a second. Then we run the standard brand detection from computer vision from cognitive services and do a more specialized brand detection with the C# SDK from using custom vision and the custom model that we trained that we will also show you in a bit. Now brand insights, flows as, again, video indexer using based on speech and OCR, computer vision providing typical brand insights, and custom vision adding additional value through object detection. Now let's look at this demo. Now let us look at video indexer. We log into video indexer, and as you log in, you see all the different videos you have already uploaded. When you upload a video, in the background, video indexer will process those videos using resources that are part of Azure Media Services, and in the background use all those cognitive services that are used for this. But let's look at a specific example. Like this is a video that is meant to talk about basically how Azure Stack works on the edge, right? You see a car driving there, you see a Microsoft logo, the Microsoft text here, and also in the transcription of the video, the word Microsoft will appear because it's part of the voice, right? On the right side, you see insights that video indexer got into this video. You see a person that has been recognized a few times. Actually, for some reason, it got confused. It's the same person, actually. It works better when you have longer videos and maybe celebrities that can be recognized. Then you find topics. Topics are categorized sometimes in a way that's not useful. For example, here surveillance state is used. That is because we're talking about data centers and Azure Stack, and monitoring is part of, but also can be understood as surveillance. So don't take some of the findings in general from AI general approaches to be subject matter relevant for you. So monitoring is good for us. It might not be good in the surveillance state. So with that being said, let's look at brands here, right? We talked about brand detection. Microsoft is a brand we're interested in, and it was found in two places in the video by video indexer. One part is here, and as the video goes, you see the Microsoft logo here, you see it again and the Microsoft text, and as the speaker talks about Microsoft, about the solution, the logo was present there. And then again here, the Microsoft logo is nicely present. But is it all places where the logo is present? That's a big question we have to ask here. Also, what are the other insights we're getting, right? We're getting, as I mentioned, other type of insights. It has a concept of scenes, and scenes have shots, and shots have keyframes. So this hierarchy allows video editors to rapidly assemble and cut videos into useful segments. The important thing for us is keyframes, because keyframes are a good visual representation of each video, but at the same time, they're also not blurry, which is not trivial for a video that moves around. Okay, let's go back to our insights. So we had the brands, the named entities, the labels. We had the topics that were talked about, and the person that appeared in it. So video indexer by itself is great, but the question is, can we do better? And I believe we can. So we're using also computer vision, which is pre-trained to recognize occurrences of the Microsoft logo, and we also want to be more specific and optimize and detect the Microsoft logo in the wild like it would appear in many scenarios. So we used custom vision and trained with object detection based on pictures we took ourselves at the company store and in the real world of the Microsoft logo. Like you take a picture, you tag the logo as Microsoft, and then upload those into the portal. Microsoft logo, again here, and you also see it in different types of objects. as soon as it loads. Yeah, like in hats, or even on cars or badges. Yeah? Not unimportantly, some pictures are blurry, and that is on purpose. So we want to be able to also detect the Microsoft logo if it's a little bit blurry. Now let's go to an example app. I will start the example app. So we trained computer vision, we trained custom vision, and we want to use the insights that we have on that same video. So we're using Video Indexer first to get some basic insights into the video. And the example application makes a first call to Video Indexer, gets the result about the video, which is pretty much exactly the same thing what we would get from the portal. Let's look at JSON. So it has the summarized insights, which is like, okay, what keywords did you find, what sentiments were detected, what brands were detected. Here's the brand Microsoft is detected here in 2 spots, which corresponds exactly to the portal that we looked at. And here's a list of topics that were talked about. Also, this aligns with what's seen in the portal. There are a few things that are not surfaced in the portal potentially. For example, the sentiments here, the sentiment is negative or neutral or positive. I'm not asking you to remember the timestamps here, but we will see in a second that if in the video people could talk about, for example, about network isolation, and a general purpose AI might consider isolation to be negative, because in times of COVID, social isolation is not good. So isolation doesn't have a good connotation. So even though network isolation, for example, might be positive, it might not be recognized as something positive by a general purpose AI. That is why using those other recognition mechanisms to, for example, find a brand in a good spot may help us, because we might here find a timestamp based on the sentiment that we don't want to look at because we think it's negative, but in fact it might be a good spot for the Microsoft brand to occur. So, but let's look more at what happens as we process that video, right? So the images essentially get uploaded to custom vision and computer vision, and we get results back. Here there's obviously nothing detected yet, and we will hit a breakpoint as soon as something relevant will be detected. Yeah, we're seeing on the right side you see the best recognized image so far based on an internal scoring we used, and on the left side the last image that has been analyzed. Oh, here we detected something. So in this call, let's look at the result. We're using the Microsoft SDK, the C# SDK, .NET SDK, to call into custom vision, and you have a bunch of results here. Right? It's a recurrence of the Microsoft brand with a specific probability / confidence, and a bounding box marking it in the picture, right? Then we also get results back from computer vision, which is here. We found the brand Microsoft twice. Yeah, we will look at the image, why we found it twice. Yeah, let's continue here. And if you look at the images here, you see we found the Microsoft brand twice because computer vision uses both the textual representation of the Microsoft brand and the logo representation of the Microsoft brand to detect it. And then we have custom vision, who also detected the image here in this very spot on the logo in the very spot in the image. So the video will go on, but the key takeaway is that here on that timestamp, which was I think around 12, I think the 12, second 12 and so on. Oh, here, 13.55. We had a really, really good representation of the Microsoft brand. Now, if you go back to Video Indexer, for some reason, the brand recognition here was from second 17 to second 30, and from second 16 to, from 16, 1 minute 16 to 1 minute 25. So let's go to the second 13:55, and wow, yeah, that's a really disconnected environment. That's a really good shot of the video, how the Microsoft brand drives through the video. So this might be actually what we want to take. So, and the takeaway is that combining those different services, we can have a better AI solution than only using video indexer, only using custom vision, or only using computer vision. We talked about cloud-based AI, cognitive services, video indexer, and so on for a while. But what about things we can actually do on device? So let's talk about Windows machine learning. Windows machine learning follows a typical machine learning workflow. First, you start training in any type of environment, right? This could be custom vision, for example. You train and you output ONNX. We will talk about ONNX briefly. Then, when you're done with that, in your software solution, in Visual Studio, for example, you add a reference to that ONNX model. It generates some code for you. Then in your application, you call that wire up that ONNX model. And then on the execution side, Windows Machine Learning runs on several platforms on Windows. So what is the architecture? On the very bottom of it, you have this either the execution layer, which could mean the CPU, or it could be DirectML, which can run on the GPU, or potentially other DirectX devices. There's talk about, for example, using USB-based neural processing types of accelerators. Then, on top of all this, there's the Windows Machine Learning runtime, which does the magic for you. Basically, think of it like as a printer driver or a graphics driver for AI acceleration. It takes the ONNX model and maps the operations in the ONNX model to operations that work most performant either on the CPU or through DirectML on your GPU, for example. Now, this is made available through the Windows Machine Learning Runtime APIs. And on top of that, then you have either a C# application or C++ application. I removed the JavaScript application a little bit because that would have required the browser, the Edge browser that was not built on Chromium. But it was awesome when it worked. So the execution steps are you would load the learning model in the ONNX file, then get a learning model device which corresponds to the execution layer here, create a learning model session that you will be able to reuse to make those calls, do your pre-processing as necessary of the data you want to call, bind input to your call, then evaluate in the machine learning session, learning model session, get the result and do necessary post-processing. It's very straightforward. There's sample code available. Yeah. So what is ONNX? ONNX is Open Neural Network Exchange format. So it is essentially a buy-in of really large vendors, like the people who are really driving all the innovation in an AI, which is Amazon Web Services, Microsoft, Facebook open source, and a lot of hardware vendors supporting this ecosystem. Again, it's a standard format. It's like the zip file for expressing like machine learning models. Where do you get machine learning models? You could use the Azure AI Gallery, but a better place would be, if you want to get something pre-built, to go to the ONNX Model Zoo on GitHub, github.com, ONNX Models. The AI Gallery also sources from that source. So you will find very interesting things there, from even things like emotion recognition or better facial expression detection. So check it out, ONNX Model Zoo. Now, if you don't want to do that for some reason, or you don't find anything in the ONNX ecosystem, there are converters available, so you can Well, you can also download them from other places. But first, let's talk about what do I do with those models? You can look at them. You can use Netron by Lutz Röder. Lutz Röder, a lot of you might know as being the inventor of .NET Reflector. And with that Netron tool, you can just look at the flow of the data and the Onyx model. But most importantly for you as a developer, you want to look at the input and the outputs. The inputs and the outputs are described and discoverable in Netron. And of course, the tools you have available in Visual Studio will also create code stubs for that to call into that. But it is really valuable to understand this input and output data. So besides of, as I said, you can also convert from other formats to Onyx. One of them is CoreML, which is the format used by Apple in iOS. And here are some sources like github.com topics, CoreML models, and the other links that you can use to explore CoreML models that you can then convert into Onyx and use in your applications. Now, this gives you a quick overview how you can actually use machine learning on the inference side, not on the training side, on the devices accelerated and optimized on the Windows platform. Now, we're getting close to the end of our talk, and in this demo, we will be putting it all together. Based on a video that we recorded in our house, we're using computer vision to get understanding about this environment. Then we're using custom vision to train a custom model, and use finally Windows machine learning on the HoloLens device to get insights into that environment in 3D. To be precise, so we recorded a video earlier, and we're using computer vision APIs to get insights into frames from that video. Those analyzed results, we must choose information that we have seen frequently recognized objects, often enough that we can get enough information to train custom vision based on that. So we train custom vision object detection based on those frequent object types. And then we export that custom vision model to Onyx and import that model into a HoloLens application in Unity 3D. And then the application displays what it has detected as seen from the perspective when it was seen displayed as a ray on the display. This may be a little bit difficult to imagine, but you will see it in a recorded video. So in a sample application, we will process the video that we recorded in our house. Let's have a look at that video. We basically see a relatively blurry and not optimized recording of our environment as I walk around in the house. You see windows, you see lamps, you see some furniture, and as you walk around you will see that we finally get into different rooms. There's some more lamps here, some more furniture, and a TV, and a staircase. You get the idea. Now, when I want to analyze that video, I press Analyze, and it will start to process the video the same way like we processed the video in the video indexer demo where I found brands in the Microsoft video. Yeah, you see it marked a lamp, it marks some furniture, it found the lamp again, and it continues to do so as it looks and loops through the video. I take what I learn and collect all this information and save it at the end of this analysis in a huge, really big JSON file, right? It has all the information from it. It has the categories found, it has the rectangles, meaning the bounding boxes of what it detected, it has what it detected, it has the confidence, and so on. Yeah? When we're done with that step, the next step I would process the JSON, and when I process this JSON file that we just looked at, I collect the data by only picking those objects that I have seen at least 15 times. 15 is the current lower boundary when I want to use object detection with custom vision. That is how many images I need at least of a specific object type and mark it in images to be uploaded, to be trained in custom vision. Yeah. And the next step after I've done that, I would upload the tags, those tags of those objects that I've seen at least 15 times in that project. And then I upload the actual images where those objects have been seen. And then I tag those images in custom vision. And finally, let me show you how it would look like when it would have been trained completely. Now let us look at custom vision about what we just created, uploaded, and trained. You see the video has created all those images and they created the tags associated with those images. Let's, for example, choose the tag dining table and go in one of the example images. You see the dining table has this bounding box right here, the big bounding box. It also recognizes the table. So actually, computer vision that we use for the training to get the insights has categories. For example, dining table is a special category, subcategory of a table. And on the table we have tableware. Another example could be stairs. Yeah, we have seen stairs in the video. Or could be the window. Yeah, the image has a window and also there was a lamp in that image. Or here, there's a television, which is also displayed. It is not entirely perfect always. For example, in this image, this is a speaker and not a television. Sometimes you get a few miscategorizations, but overall you get really valuable insights into your environment doing that completely automated. Now, let's say we did the training, right? So how do we get the model? Get the model here, and you click on export, and you would say Onyx and save that model. We're using the full Onyx version here, not the Float 60 version right now, but we can also use the Float 60 version. It differs in performance on the platform you execute it on. Float 16 should run a little bit faster on most platforms. And after we've done that, after we exported the Onyx model, we now would use it in a Unity application that we prepared. Unity is a game development environment that uses C# natively to for software developers to write code to interact with gaming objects or 3D objects. Yeah. And so we dropped that model that we exported into a folder, and we're able to load it from that folder, which is not part of the demo, how we load it from Unity and so on. And I will also not show you the Windows machine learning code right now, because we just don't have the time. But we have the model and we have the labels. If you open the labels, you see it's just a text file, and it has all the categories that we have seen in custom vision. And well, after we've done all this, we can look at the we can install that application on HoloLens and show you how it works. So this is the recorded video, the example video of the last step of the demo. As I walk around, did you see here the television got recognized? It got recognized a few times. And you have all those arrays in the environment. For example, here, it recognized seating here, it recognized seating there. There's another seating right here. There's a window here in the back, and you see also the other colors of the rays. Those other colors basically describe the bounding box. You see it here, like the how you look at the whole object that you're recognizing. There will be one ray that points right into the middle of the object, and then every corner of the object, as it was recognized, will also have a ray associated with this. This is now, I've been walking a little bit faster. Sorry, I hope you don't feel sick looking at the video. But let's wait to recognize anything else. Yeah, so you see it recognizes the stairs, and the boundary of the stairs are those colored rays here. We have the stairs here marked right in the middle, and as those rays converge is a point of view that we had exactly in the upper right corner from our perspective right now, where we have seen the stairs. This matters as you walk around in a 3D environment, things present differently depending on the angle we look at things, and this will basically record that angle we looked at those stairs and mark precisely where we have seen those stairs. Now, you can think of it a little bit further, that over time we can get rich understanding of the environment we're walking in with. Like we could basically create a heat map of what have we seen, how often, exactly where, and mark a whole environment this way. The applications for this are very, very rich. So you don't need a cloud connection anymore. Admittedly, with a cloud connection, we would get even more insights, but what if we don't have it, right? So without the cloud connection, we would be able to have now a customized model that's optimized for the environment that we're in. So we know the camera we're using, we know the lighting conditions we're using, and we know also the objects we're expecting because we recorded the video that we trained on in that same environment. That is very, very specialized indeed. But it really allows us to have then a machine learning, a deep learning based model that we can run on our devices, that we recognize things in our real world as you would see them before. Applications could be in a museum where you want to present information about things you see there, or assisted applications that help people with visual disabilities, or inventory of a building to get an idea where specific objects are that they haven't been moved. I hope that gives you an overview, and the capabilities of this approach would only get bigger, the bigger also the computer vision capabilities are that we use initially to train our model to learn about the environment. Now we put everything together, and well, I hope that gives you a good understanding of what you would be able to do in real 3D space if you use several cognitive computing, cognitive services capabilities together and combine them in an application. You get real understanding of your three-dimensional environment, and this enables spatial computing of the next generation. My name is Andreas Erben, and I thank you. Vielen Dank. My contact information is here. Do not hesitate to reach out, and do not hesitate to ask questions. I don't bite. I will hang around to you for a while here, and you can also ask me questions after this talk is over. Have fun at DPS, and great to be with you here.